Magnetars are the most magnetic objects in the known universe, born from the collapsed cores of massive stars. Imagine a celestial object so powerful that it could wipe every credit card on Earth from halfway to the moon. A magnetar is only about 20 kilometers or 12 miles wide, but it contains more mass than our entire sun. Its magnetic field is 1,000 trillion times stronger than Earth's magnetic field, which is powerful enough to dissolve your very atoms if you got within 1,000 kilometers or 620 miles of its surface. Welcome to the extreme world of magnetars, the most dangerous stars in the universe. Today we are investigating the extreme physics of these strange remnants, diving into the most intense magnetic fields ever discovered by modern science. Space is filled with bizarre and terrifying objects, but few can match the sheer destructive capability of a magnetar. They lurk in the dark corners of our galaxy, spinning rapidly, glowing with intense radiation, and occasionally erupting with bursts of energy that can be felt across thousands of light years. To understand how such a monster comes to exist, we have to look back at the life cycle of the most massive stars in the cosmos. Not every star has what it takes to become a magnetar. Our own sun is far too small. When a star that is at least 8 to 20 times more massive than our sun reaches the end of its life, it runs out of nuclear fuel. For millions of years, the outward pressure of nuclear fusion balances the inward crush of gravity. But when the fuel runs out, gravity wins instantly. The core collapses inward at a fraction of the speed of light, crushing the atoms so tightly that electrons and protons are smashed together to form neutrons. This sudden collapse triggers a massive shock wave, resulting in a supernova explosion that blows the outer layers of the star deep into space. What is left behind is a dense, incredibly hot sphere of pure neutrons. This is a neutron star. A typical neutron star packs about 1.5 times the mass of our sun into a sphere, just 20 kilometers or 12 miles across. The density is almost impossible to comprehend. A single teaspoon of neutron star material would weigh about 1 billion tons on Earth, which is roughly the weight of Mount Everest. But a magnetar is not just any neutron star. It is a very special, very rare variant. Out of the thousands of neutron stars we have discovered, only a few dozen are confirmed to be magnetars. What sets them apart is their unimaginably powerful magnetic field, and the secret to that field lies in the exact moment of their birth. When a massive star collapses, its rotation speeds up dramatically, much like a figure skater pulling in their arms to spin faster. Some newborn neutron stars spin hundreds of times every second. At the same time, the newly formed core is violently churning with convective fluids, acting like a giant cosmic dynamo. If the spin rate and the convection match up perfectly, they can amplify the original magnetic field of the star to astronomical levels. Earth's magnetic field is about 1 Gauss. A refrigerator magnet is about 100 Gauss. A standard neutron star has a magnetic field of about 1 trillion Gauss. But a magnetar has a magnetic field that reaches up to 1 quadrillion Gauss. This is the absolute upper limit of magnetic strength in the known universe. The magnetic field of a magnetar is so intense that it fundamentally alters the physical properties of the vacuum of space around it. According to the laws of quantum mechanics, empty space is never truly empty. It is boiling with virtual particles that pop in and out of existence. A magnetar field is so strong that it forces these virtual particles to behave in strange ways, causing light itself to split and polarize as it travels near the star. This effect, known as vacuum birefringence, was once only a theoretical prediction, but astronomers have now observed it in the light coming from a distant neutron star. What would happen if you somehow found yourself near a magnetar? The danger would not just come from the crushing gravity, though the gravity is 100 billion times stronger than on Earth. Long before you even reach the surface, the magnetic field would destroy you at a fundamental level. At a distance of 1,000 kilometers or 620 miles, the magnetic force would begin to overwhelm the electromagnetic forces that hold your atoms together. The electron clouds that orbit the nuclei of your atoms would be stretched into thin, shaped like needles, cylinders. The chemistry of life relies on the specific shapes of molecules, but near a magnetar, all molecules are distorted beyond recognition. The bonds between atoms would break, and your entire body would dissolve into a cloud of elongated subatomic particles. Even water, the fundamental building block of life, would become a highly toxic, strange substance under these conditions. But the danger stretches much further than 1,000 kilometers, or 620 miles. As mentioned earlier, if a magnetar were placed halfway between the Earth and the Moon, roughly 190,000 kilometers, or 18,000 miles away, its magnetic field would instantly erase every magnetic stripe on every credit card, every computer hard drive, and every piece of magnetic storage on our planet. It would scramble the navigation systems of airplanes, disrupt the communication satellites, and cause massive electrical surges in our power grids, plunging the entire world into a dark age. Magnetars do not just sit quietly in space. They are highly active and incredibly violent. The surface of a magnetar is a solid crust made of a dense lattice of neutrons and exotic particles. This crust is constantly subjected to immense stress from the overpowering magnetic field inside the star. The magnetic field lines are twisted and tangled by the rapid rotation, building up an unbelievable amount of tension. Eventually, the crust cannot handle the strain anymore, and it cracks. This event is known as a starquake on Earth. Earthquakes are caused by tectonic plates shifting, releasing energy that shakes the ground. A starquake is conceptually similar, but the scale of energy released is beyond human comprehension. When the crust of a magnetar cracks, it sends a sudden, violent jolt through the magnetic field, snapping the magnetic field lines and releasing a colossal burst of energy in the form of X-rays and gamma rays. These eruptions are known as soft gamma repeaters, and they are among the brightest explosions in the universe. A single flare from a starquake can release more energy in 1/10 of a second than our sun will emit in 100,000 years. The sheer power of these starquakes was vividly demonstrated on December 27, 2004. On that day, a wave of gamma rays washed over our solar system. The radiation was so intense that it blinded several space telescopes and physically altered the upper atmosphere of Earth, causing it to expand. Astronomers quickly traced the source of the blast. It came from a magnetar known as SGR 1806, located about 50,000 light-years away, or roughly 300 quadrillion miles away, on the other side of the Milky Way galaxy. Despite being incredibly far away, the flare was brighter than the full moon in the gamma-ray spectrum. It was the brightest event ever recorded originating from outside our solar system. If SGR 1806 had been located within 10 light-years, or 58 trillion miles of Earth, the flare would have severely damaged our ozone layer, triggering a mass extinction event by allowing lethal ultraviolet radiation from the sun to sterilize the surface of our planet. Thankfully, there are no magnetars that close to us. The nearest known magnetar is thousands of light-years away, keeping our fragile biosphere safe from their devastating power. Despite their incredible power, magnetars have relatively short lifespans on the cosmic scale. The intense magnetic field that defines them is also their downfall. As the magnetar spins, its magnetic field drags through the surrounding space, emitting constant streams of radiation and particles. This process acts like a giant brake, draining the rotational energy of the star. Over the course of about 10,000 years, the magnetar slows down significantly. As its spin decreases, the magnetic field begins to decay and weaken. Eventually, the starquakes stop. The gamma-ray bursts cease, and the magnetar settles down into a quieter, more ordinary existence as a standard neutron star. Because of this short active period, astronomers believe that there could be millions of dead magnetars scattered throughout the Milky Way, silent remnants of a violent past. The fact that we can see any active magnetars at all means they must be constantly replenished by new supernova explosions. It is a continuous cycle of creation and destruction, playing out over billions of years. In recent years, magnetars have become the prime suspects in one of the greatest mysteries in modern astronomy, the origin of fast radio bursts. Fast radio bursts, or FRBs, are incredibly brief, intensely bright flashes of radio waves that originate from deep space, often billions of light years away. For a long time, astronomers had no idea what could produce such a massive amount of radio energy in just a few milliseconds. But in 2020, a breakthrough occurred. A fast radio burst was detected coming from inside our own Milky Way galaxy, and it was traced directly to a known magnetar. This discovery strongly suggests that starquakes on magnetars, or perhaps magnetic reconnections in their magnetospheres, are the source of these mysterious signals. The sudden snapping of magnetic field lines could act like a cosmic whip, accelerating particles to near the speed of light and blasting a beam of radio waves out into the universe. It is a thrilling confirmation that these extreme objects are responsible for some of the most dramatic phenomena we can observe. For physicists, magnetars are more than just dangerous stars. They are the ultimate cosmic laboratories. We cannot recreate the conditions of a neutron star or a magnetar anywhere on Earth. The temperatures, the pressures, and the magnetic fields are simply too extreme. By studying the light and radiation emitted by these stars, scientists can test the fundamental laws of physics. We can observe how matter behaves when it is compressed to its absolute limit. We can study the nature of gravity in the most extreme environments, testing the boundaries of general relativity. We can explore the strange quantum mechanical effects that occur in super-strong magnetic fields. Every time a new magnetar is discovered or a new flare is recorded, we gather vital data that helps us unlock the deepest secrets of the universe. Current missions like the James Webb Space Telescope and advanced X-ray observatories are constantly scanning the sky for these elusive objects, mapping their fields and measuring their temperatures. Deep beneath the cracking crust of a magnetar, physicists believe that an even stranger realm exists. The pressure at the very center of the star is so immense that even neutrons might not survive intact. Some theoretical models suggest that the neutrons themselves are crushed, dissolving into a soup of free quarks, the fundamental building blocks of matter. This hypothetical state of matter is called quark matter or strange matter. If strange matter exists inside a magnetar, it would mean that the core is entirely detached from the normal rules of chemistry and atomic physics. This ultra-dense quark plasma would be incredibly conductive, allowing electrical currents to flow with absolute zero resistance. A frictionless superconducting core could be the key to maintaining the terrifying magnetic field over thousands of years. Without this superconducting interior, the immense electrical currents generating the field might simply dissipate. Every time a magnetar undergoes a starquake, the resulting vibrations ring through the star like a bell. By studying these seismic waves, astronomers are mapping the deep interior, hoping to confirm the existence of strange matter. As we look toward the future of astronomy, new tools will drastically enhance our ability to study these magnetic titans. Next-generation radio telescope arrays are being constructed to monitor the sky continuously for the sudden bright flashes of fast radio bursts. When the next magnetar flares up in our galaxy, we will be ready to catch every microsecond of the event. Furthermore, advanced gravitational wave observatories are being upgraded to detect the subtle ripples in space-time caused by deformed, spinning neutron stars. If a magnetar is slightly asymmetrical, its rapid rotation could generate a continuous faint hum of gravitational waves. Detecting this hum would provide direct evidence of the immense strain on the crust, proving just how much the magnetic field distorts the physical shape of the star. Spacecraft designed to measure the polarization of X-rays will allow us to see exactly how the magnetic field warps the light leaving the surface. These future missions will turn theoretical mathematics into observational facts, cementing their reputation as the ultimate cosmic enigmas. The hunt for magnetars is a challenging endeavor because they are so small, only 20 kilometers or 12 miles across. They do not emit a lot of visible light. They are virtually invisible to traditional optical telescopes. Instead, we have to rely on specialized instruments that can detect the high-energy X-rays and gamma rays they produce. Space agencies around the world are developing new, more sensitive detectors to find these hidden monsters. As our technology improves, we are beginning to discover magnetars in different stages of their life cycle, helping us piece together the complete story of their evolution. We are finding them in the remnants of recent supernovas, surrounded by glowing clouds of expanding gas. We are finding older ones that have begun to quiet down, their magnetic fields slowly fading away. Each discovery adds a new chapter to our understanding of the cosmos, reminding us of the incredible diversity and violence of the universe. Magnetars represent the absolute extremes of nature. They are born from the explosive death of massive stars, forged in the most violent events imaginable. They possess gravity so intense that it crushes matter into pure neutrons, and magnetic fields so powerful that they tear apart the very fabric of space and time. They are capable of unleashing blasts of energy that can cross galaxies and alter planetary atmospheres. Yet, despite their terrifying power, they are essential pieces of the cosmic puzzle. They help us understand the life cycle of stars, the origins of mysterious radio bursts, and the fundamental laws that govern the universe. The next time you look up at the night sky, remember that hidden among the peaceful twinkling stars are dark, spinning magnets of unimaginable power, quietly waiting for their next violent eruption. We will continue to watch, listen, and learn from these incredible objects, pushing the boundaries of human knowledge further into the dark unknown. Thank you for joining us on this exploration of Magnetars, the most dangerous stars in the universe. Keep looking up and stay curious about the wonders of deep space. Thank you for watching. I really would appreciate it if you would subscribe, follow, like, and comment, as this helps the algorithm know that people are interested in my videos.